発車まで5分ほどお待ちください。
Software. How do we think about this? How components interact. And this drives all of our software. We're not working with distributed systems. We've got logic concurrent systems. To do anything in scale, it involves things interacting. One of the best places we have for good examples of this is that Internet engineering. Suppose we had protocols specified for how different components work. This is the backbone of the Internet, how it works. I love some of the different RFCs that they put out the 1st of April every year. They put out a fun RFC. One of my favorites is advertising common control protocol. It's really successful coverage. And this is kind of fun. It's something that I used to learn from them. Some of these codes like, sure, well, it means continuing to handle just as we do some of these functions. And the interesting one is this. So all of those piece. So I think this one. This is the best explanation I've ever seen for it. The origin of the words that are used in that beginning of the Little Endian basically comes from Gulliver's Travels and Adventures in Lilliput, where the people went to war over which end of your egg do you eat first. You beat the big end or the little end? Is that the way you eat your eggs? So Endianness comes from that. But this explains some of that history, but also the origin of a lot of computer science and why we encode integers the way they are, done in an incredibly fun and really great way to read. So that's a big one to go find against. It's the 1st of April 1980. I'm guessing many people in this room were even born after that. Another big one is the transmission of IPs in Indian characters. So pigeon house to do different things. That was back in 1990. That was updated with quality of service later on, and eventually, well, recently for IPv6. Easy learning some of this stuff can be quite good fun. It's kind of nerds, but there's lots of things we can learn from some of these things in our history. Should we document our protocols is kind of an interesting question. I love to document protocols on my projects because I think it just helps my own thinking, it helps me realize how to work my way through stuff. And particularly I find this to be a very often come up as API versus protocol. Basically, I think an API is very anemic. It's a very two-dimensional view of something. It doesn't really cover most of what's important. And most important to me in this is precedence, order in which you do things. Not as much more. So if you think about an API, it doesn't tell you anything about precedence. It tells you what functions it can perform, but it doesn't say which order they should be performed. It doesn't say what are exceptions for things that are interesting. So let's take a simple example. So let's say I have a file system, and I want to interact with a file. What is my protocol? I'm allowed to interact with a file. I can publish an API, but it doesn't tell me as much as doing something like this. Let's say if I use a file, I can perform a number of operations on it. People tend to do things like this, like a pseudo-regular expression language, where I can open a file, I can follow it by 0 or read or write operations followed by a close. That's totally what the precedence is. And for files, we take that as kind of obvious. It's not an API you're using every day. How do you know the orders in which you should use it? What do you mean? If you call this and throw an exception in, you end up reporting bugs. So you should call this something first. Well, you actually just documented the order in the first place. It's a bit much easier to do. And so you can then just expand it as give the order which things are called, list each of the functions. That's great. I find it's so much more useful way to design an interface with the system. Here we go. But kind of important as well, when you perform any one of these actions, this question is really important. What can possibly go wrong? I've had the pleasure of working with the guy who's worked on a lot of systems that are very important, like people die if the systems don't work, or they take somebody else's servers and send stuff into space. Then you think about your software, creating code, so it's all you have to do. These things, this kind of thing, so you start thinking carefully about what can possibly go wrong, how to get stuff go right. And it's actually one of the biggest causes of software failures we have. This report here is a great read, if you haven't already seen it. It explores what was the things that were behind mutual purchase, but 25% of the orders they were many of the exceptions that were there to do in the exception handlers, we should fix this before we go into production. These are real code of conduct. If you allow you to release software that you know those sorts of problems are in, that's not very professional. So it's kind of interesting how you go forward with this. So let's look at design a protocol and look at a realistic example of something more complicated and how we could approach it. And this is kind of where I find it's interesting between those who have a background in some of how the world works, how larger scale systems work, and come up with much more interesting algorithms than typically the nerds who only ever worked on their own. Because I think if your whole sphere of influence, your reference frame for the world is very narrow, it means you've got a very narrow view of what you can come up with. So multicast protocols are fascinating for this because you're dealing with sending data from one point of many points to many points. So it's a complicated interaction. It's not just a point-to-point simple thing. And if you want to design a protocol where you're going to send out data from a single source and it's going to go to many receivers, the data can get lost on the way. How do you realize that the data has been lost, and how do you end up recovering what's a protocol you go through for that? Do you try to centrally coordinate it? Do you try to do something different in there? And this has been a problem that's been faced a number of times. And as you do it, you end up with some very obvious problems if you try to implement it. So one of them is ACK implosion. So if you realize that data can be lost, one of the ways you deal with it is you give an acknowledgement, positive acknowledgement that you've got the data, and that's what it is. The problem is that doesn't scale up because if you get more receivers, that's more things hacking. So then the source can't cope with that, you get a scaling problem. The other side of it you can go with is, well, let's send negative acknowledgements because we'll assume it will work most of the time, and if it doesn't work, we'll send the NAC and recover it back. But that does work with data, it still has some problems because the source tends to be correlated. Some network device along the way has a power overrun and it starts to drop data, and that means everybody who'll be downstream from that doesn't get the data, so they'll all NAC, and you end up overcoming the source. So we end up with this NAC implosion. Now there's many implementations and approaches to solve this. And the first name on this paper is Sally Floyd. Her and Von Jacobson are behind an awful lot of what made the internet successful. And this one